Okay, so we're going to talk more now about potential and kinetic energy. To begin with, we're going to discuss something that's called a conservative force. And a conservative force is one in which the work done is independent of the path taken. Example, gravitational force. So we saw an example of this in the previous video and the last example that we did where we had a roller coaster and it went down 25 meters and then it came back up 5 meters. So we only had to use the starting and ending point in order to calculate the potential energy. A non-conservative force, on the other hand, is a force in which the work done depends upon the path taken. And a good example of this is friction, and we'll discuss more about this later on in this video. Okay, so another kind of potential energy. Potential energy is stored in the spring. Now, before we get into that equation, we need to talk about something that's called Hooke's law. Hooke's law is very simple. All it says is that the more you stretch a spring, the more force you're going to have to apply on the spring. So the equation is F is equal to K delta X, where delta X is the displacement that the spring is stretched, and K is something that's called the spring constant. So this is related to how stiff the spring is. So you can imagine, for example, that a pen spring has got a relatively low spring constant, where one of those big shock absorbers in a car have much greater spring constant. Units are newtons per meter. Okay, so just a quick example of Hooke's law. If you've got a 500-gram mass and it stretches a spring 2 centimeters, what's the spring constant? We solve for K. F is going to be the weight of the mass, so that's 0.5 kilograms times 9.8. And delta X is the amount that the spring is stretched, 0.02 meters. So that comes out to be 245 newtons per meter. Okay, now we know that work is equal to force times distance, and we're going to use X here instead of D because we're going to do a little substituting here. So the average force to stretch a spring is Kx over 2. Now the reason why it's Kx over 2 is because the more you stretch the spring, the more force you're going to have to apply. So it's not a constant force. So to stretch it a little bit, a smaller force, a little more, a bigger force. So the more you stretch the spring, the more force you're going to have to apply. And so Kx over 2 would be the average force to stretch the spring a distance K. So we're going to substitute that into this work formula, and so we get 1/2 K times X squared. And that's the work, so the potential energy is equal to the work done, or 1/2 Kx squared. The force applied to stretch a spring is also an example of a conservative force. Now, the conservation of mechanical energy says that when conservative forces apply, the total mechanical energy of a system stays constant. Or another way of saying that is the sum of the kinetic and the potential energy initial must be equal to the sum of the kinetic and potential energy final. Now, this potential energy might be energy stored in a spring, or it might be gravitational potential energy. Okay, so here's an example. We've got a 5 kilogram subway train. It's brought to stop from a speed of 0.5 meters per second in 0.4 meters by a large spring bumper at the end of the track. What's the force constant of the spring? So we're going to start with this equation up here. And in this case, the initial potential energy is 0 because it doesn't have energy stored in the spring or any gravitational potential energy. And then it's brought to rest, so the final kinetic energy is 0. So substituting the zeros in the appropriate place, we get that. Or, remember, kinetic energy is 1/2 mv squared, so 1/2 times the mass of the subway car times its velocity squared equals, now this is potential energy stored in the spring, 1/2 kx squared, so 1/2 k, the displacement at the spring is compressed, in this case is 0.4 meters. So we solve for k, and we end up with 7.81 times 10 to the 5th newtons per meter. Okay, so here's another example. We've got a rock that's on a 50-meter cliff, falls off. We want to find the velocity of the rock 5 meters from the ground using energy principles. Okay, so we start out with the same formula as before, and in this case, the rock is initially at rest, so its initial kinetic energy is 0, but at that location 5 meters from the ground, it does have both kinetic and potential energy at that point. So our equation, this is 0. We take the mass of the rock, which we don't know, times g, times 50 meters, and that equals the final kinetic energy, 1/2 mv squared, plus the final potential energy, m, times 9.8 times 5 meters. Now notice that we don't need to know the mass of the rock because that divides out on both sides of the equation. So we solve for v. We got the square root of 2 times 9.8 times 50 minus 9.8 times 5. So we work through the numbers there, and we end up with 3 times 10 to the 1 meters per second. Notice I'm writing it like that because there is only 2 significant figures in the answer. I don't want to write it as 30 because that would indicate only 1 significant figure. Okay, now, non-conservative forces. Non-conservative forces tend to remove mechanical energy from the system because work has to be done to overcome friction. So we can use this form of an equation when we're dealing with non-conservative forces, and that is that the initial kinetic energy plus the initial potential energy minus the work done in overcoming friction is equal to the final kinetic energy plus the final potential energy. Here's an example that uses non-conservative forces. So we've got a 500 kilogram roller coaster. It starts from a height of 40 meters from the ground. It descends a track and then travels up a second hill, so it goes down and then comes back up a second hill, only reaching a height of 25 meters where it comes to rest. We want to estimate the thermal energy, or the heat, produced as a result of friction. So we start out with the same equation that we that we used in the last slide, and we want to solve for the work due to friction. So the work due to friction is equal to the initial kinetic plus the initial potential minus the final kinetic plus the final potential. Okay, so the initial kinetic is 0, and the initial potential is 500 kilograms times 9.8 times 40 meters, minus the final kinetic is also 0 because the roller coaster came to a stop, plus 500 kilograms times 9.8 times 25 meters. So we work through those numbers. We come up with 7.35 times 10 to the 4th joules. This would be the amount of energy that was used to overcome friction, and it would show up as heat. All right, now the conservation of energy, and I'm sure you've heard of this before, states that energy can't be created or destroyed, but only converted from one form into another. Another way of saying that is that the total energy of the system remains constant. Now, this is all forms of energy. So it may include thermal energy, it may include the mechanical energy that we've been talking about, and other forms of energy such as electrical energy, nuclear energy, chemical energy, and many others. There's more details and further explanation of this in your text, which you should look at. Power is the rate at which work is done. And anytime you've got that word rate in there, there's going to be time. So power is equal to work, W, divided by T. Units for power are joules per second, and a joule per second is defined as a watt, and a watt is also can be expressed as a kilogram meter squared over second cubed. So it's essentially kilogram meter squared per second squared, which was the joule divided by a second. So that's where the second cube comes in. You may have heard horsepower. 1 horsepower is equal to 746 watts. So they're both units of power. Now, if you take this equation here and you solve it for work, then work is equal to power times time. And by the way, I'm saying work, but this could also be energy. So work or energy is equal to power times time. Now, a kilowatt hour, if you ever looked at your electric bill or your parents' electric bill, you may have seen that electrical energy is often expressed in that unit. And it's a unit of work or energy. It's not a unit of power, it's a work of energy, unit of energy. And that's because work is equal to power times time. So the kilowatt is a unit of power, and the hour, of course, is a unit of time. Now, you can actually convert a kilowatt hour into joules, because a kilowatt is 1,000 watts, 1 times 10 to the third, times an hour, which is 3,600 seconds. So that's 3.6 times 10 to the 6 watt seconds. But a watt second is the same as a joule. So 1 kilowatt hour is 3.6 times 10 to the 6 joules. A simple example, using power, we want to calculate the power generated by a 60 kilogram jogger who ascends a flight of stairs 3 meters high in 2.5 seconds. So the power is equal to the work that he does divided by the time. Now the work that he does is going to be equal to his weight, which is 60 kilograms times 9.8, times that vertical distance that he ascends, which is 3 meters, and we're going to divide that by the time. So that comes out to be 7.0 times 10 to the second watts. Notice that is just a little less than a horsepower. And lastly, a very practical kind of problem here. What is the cost of operating a 0.2 kilowatt computer 6 hours per day for 30 days if the cost of electricity is 0.12 cents essentially per kilowatt hour? So the energy used in kilowatt hours is going to be 0.2 kilowatts times 6 hours per day for 30 days. So if you multiply that all through, that comes out to be 36 kilowatt hours. So we take the 36 kilowatt hours, we multiply it by the 12 cents per kilowatt hour, and that results in $4.32 would be the cost. Now, one thing I just want to reiterate here, that a watt is a unit of power. It's not a unit of energy. Okay, the watt is a unit of power. The watt second is a unit of energy. The kilowatt hour is a unit of energy. But the watt is a unit of power. So when you hear about, for example, wind turbines that tell you how many gigawatts they are, how many megawatts they are. That's telling you the rate at which they can generate energy.